Hi guys, today we're going to have a quick little lesson on half-lives. And half-life is defined as the time that's required for a quantity to reduce to half of its initial value. It's a topic that we use in chemistry and earth science and some other sciences too. And today I just want to show you guys the basic concept and how to do some simple half-life calculations. So the idea is if you have a compound that is radioactive, it would decay at a predictable rate. And if you know that rate, called the half-life, then you can predict into the future how much would remain as time goes on. So on this table here, I just wrote down some common isotopes and their half-lives. And as you can see, they're all different. So every radioactive isotope has a different half-life. A really common one that we use in earth science a lot is carbon-14. That has a half-life of 5,730 years. But if you look at some of these other ones, uranium, thorium, they're way longer. So uranium takes 710 million years to decay to half of its original value. Thorium takes 14 billion years, which is basically the age of the universe. So that one decays very, very slowly. But there's also ones that decay very quickly. Lithium, for example, lithium-8, only takes less than a second to decay to half of its original value. So half-lives are kind of all over the place. But what I want to show you guys now is just how can we do a basic half-life calculation. So let's say, here's a problem that you might find in an earth science class. It says if you have 200 grams of carbon-14, how much would remain after 17,190 years? And then it gives us the half-life of carbon-14 as 5,730 years. So there's a couple ways that you can do this problem, but a really simple way that I use a lot in class is to make yourself what I call a time mass chart. And this is just a little chart that we can kind of keep track of what's happening as we predict into the future. So let's always start at time 0, which you can think of as the present or your starting spot or whatever you want to call it. But in this problem, at the present, we are starting with 200 grams of carbon-14. And since we're going to be predicting into the future, our job is to figure out how much is left after 17,000 years. We're going to go down in the time column, and we're going to move in jumps of 5,730 years, because that represents one half-life. So the first thing we'll write down here is 5,730 years. And that represents one half-life. So by definition, after one half-life, we will have half of the original mass. So that puts us at 100 grams. Now we're going to keep on going. So our next jump is going to be we're going to add another 5,730 years. So that'll get us to 11,460 years. That represents two half-lives. And at that point, we would cut that mass, that 100, in half. So now we're down to 50. Notice we didn't go to 0 here, because it's not simply subtracting 100 each time, it's taking half of the previous mass. So this time we only really lost 50 grams. Let's keep going, because our job is to get to 17,000. So we're almost there. The next jump would be 17,190 years. Once again, I'm just adding a half-life each time, 5,730 years. That's 3 half-lives. And at that point, we would now be down to 25 grams. And for this problem, that's it. Our answer is 25 grams. Starting with 200, going into the future, 3 half-lives, 17,000 years, gives us 25 grams. Let's try one more problem. So let's try this one now. So this is basically the same concept, it's just worded a little differently. So I wanted to close by showing you guys how to do this one. So in this case, still carbon-14, but this time it's asking us how long would it take a sample to decay to the point that 6.25% of the original carbon remains. So this time we're solving for a time rather than a mass like we were on the first one. But we'll solve it in a similar way. We'll make our time mass chart. But the difference from the last problem to this problem is notice that they're talking about percentage. Right, in this first problem, just to go back to this first one for a second, they started us off in grams. But this one, we're talking about percent. So if the problem words it with percentage, under your mass, just start at 100% and still start at 0 right at the present. And then we're just going to go down from there. So it's still carbon-14, so every half-life is still 5,730 years. And we just cut the mass in half. So we would cut it to 50%. And we're just going to keep on going. So 11,460 years gets us to 25%. Then we would go another half-life. So that would be 17,190 years. And that's going to get us to 12.5%. And we're getting pretty close now. We just have to go one more half-life. So that's going to be 22,920 years. And we cut that in half, and we get 6.25%. And that should do it for us. We were looking for how long does it take to get to 6.25. There's 6.25. Boom, there's our answer, 22,000 years. Or you could think of it as 1, 2, 3, 4 half-lives. So there's some simple half-life problems. Hope that was helpful.